All right, let's get right into it. You know, for years, the whole field of mechanistic interpretability has been wrestling with this one huge task, trying to read the mind of an AI after it's been trained. But what if we could do the complete opposite? What if, instead of just reading, we could actually write? Now that is the incredible question at the core of a new paper from George Wang and Daniel Murfet called Patterning, the Dual of Interpretability. And this slide just nails the shift in thinking here. On one side, you've got interpretability. Think of it like archaeology, right? We're digging through a model that's already built, trying to piece together how it works. But on the other side, you have patterning. This is about being the architect from day one. It asks, hey, if we want an AI to have a very specific internal circuit, can we design the training data to build exactly that? It's a huge leap from just watching to actually taking control.
So here's our game plan for this explainer. First, we'll set the stage, talking about the problem patterning is trying to solve. Then, we'll dive into the theory behind it. After that, we get to the fun part. 2 really elegant experiments that show this thing in action. And we'll wrap up by looking at what this could mean for the future of AI.
To really get why this is such a big deal, we need to understand where we are right now. And honestly, the challenge of interpretability is just massive. We're talking about trying to understand systems with billions, sometimes trillions of parameters. It's like we're hunting for the ghost in the machine. So basically what we do now is we train a model, and then we go in with our virtual scalpels and dissect it. We're hoping to find these things called circuits that explain what it's doing, like the famous induction circuit that helps a model spot and continue patterns. It's an amazing diagnostic tool for sure, but it's fundamentally reactive. We can only study what the training process has already cooked up. And this is where patterning just completely flips the script. Instead of just finding circuits that already exist, the whole point is to build them on purpose. It's trying to create a real science of control over a model's internal logic while it's learning. The definition here is so simple, but also just incredibly ambitious. Let's say you want your model to generalize in a very specific way, like you want it to use a robust, logical algorithm instead of some flimsy shortcut. Patterning's goal is to give us the exact recipe for the training data that will bake that algorithm right into the model's core. Okay, I know this looks a little scary, but hang with me, because the idea behind it is actually beautiful. Think of this equation like it's a GPS for AI training. On the right, that demute target is your destination. It's the specific change you want to make to the AI's internal wiring. On the far left, DHOpt is the step-by-step driving directions, the exact tweaks you need to make to your training data. And that chi symbol in the middle, that's the magic. It's the map that translates your destination into the perfect route to get there. So that C symbol stands for susceptibilities, and they are the absolute key to this whole thing. Here's a way to think about it. If a model's circuit is a muscle, susceptibility tells you exactly which exercises, which specific examples in the training data make that muscle stronger. It measures the tiny, precise influence of every single data point on every internal part of the model. Patterning just flips that around. If you know which exercises build a muscle, you can design the perfect workout plan from the start. So, that's the theory, but does it actually work? Let's look at a real experiment. The first test is a direct proof of concept. Can patterning actually control the formation of that famous induction circuit we talked about in a small language model? Can you literally turn it up or down, like a volume knob? This slide shows you exactly what they were targeting. What you're looking at is text from the training data. The highlights are showing what are called induction patterns, these repeated phrases that are known to build the induction circuit. Using those susceptibilities, the researchers pinpointed these kinds of patterns as being super important. So the goal becomes pretty simple. What happens if we mess with how often the model sees these patterns, but in a really precise way? And the results are just wow, crystal clear. On the right, that's the model trained on the special pattern data, where they deliberately downweighted those key repeating phrases. The vertical axis is measuring the strength of the induction circuit. And just look at it. It's basically a flat line. They completely stopped the circuit from ever forming. They turned the dial all the way down to 0. And then, of course, they did the exact opposite. They cooked up a new dataset that cranked up the number of those induction patterns. And look at the result on the right now. The curve just shoots up way higher and way earlier than the regular model. They didn't just build the circuit, they made it form faster and stronger. They turned that dial up to 11. So the takeaway from this first experiment is just a resounding success. They showed they could have precise, directional control over a specific, well-known mechanism inside a neural network, all just by reweighting the training data in a super principled way. Okay, but turning a single circuit up or down is one thing.
Can patterning handle something more abstract? Can it actually force a model to choose one entire problem-solving strategy over another?
To test this, they came up with this really clever task: balancing parentheses. Now, they designed the training data so that two totally different algorithms could get a perfect score. The nested algorithm is the right way to do it, the one that actually generalizes. The equal count algorithm is just a lazy shortcut that happens to work on the training data, but fails on harder examples. So the big question is, can you use patterning to make the model learn the right algorithm and ignore that tempting shortcut?
Now, to do this, they pulled from this fascinating area called singular learning theory. The core idea is that when a model has a few different ways to solve a problem for the same score, it has a built-in bias towards the simpler solution, and you can actually measure this simplicity mathematically. The goal then was brilliant. Use patterning to tweak the training data to make the lazy shortcut look more complicated to the model, and make the correct, robust algorithm seem like the easiest, most natural path to take.
And this chart, this shows the incredible payoff. These bars show how well the models did on new data where the shortcut just doesn't work. With the original data, it was a toss-up. But look at the almost nested dataset on the right. This is where they used patterning to make the good algorithm look more attractive. The accuracy nearly hits 50%. And even more amazing, in the almost equal dataset, they patterned it to specifically punish the bad algorithm, and the accuracy just craters. They didn't just cross their fingers and hope for the best. They actively reshaped the learning process to guide the model to the right answer.
So we've seen that this stuff actually works. But what does it all mean for the big picture? I mean, this is about way more than just building little circuits in small models. This could be a totally new way to think about AI control.
The paper uses this fantastic analogy from biology. Think about the training data like it's the chemical soup an embryo develops in. You know how a tiny change in chemicals can tell a cell to become part of an eye instead of a wing? The idea here is the same. Small, targeted changes in the data distribution can steer a neural network to develop one kind of internal structure instead of another. And this, right here, brings us to the grand challenge of AI alignment. Most of our methods today try to shape a model's behavior from the outside in by carefully filtering what it says. Patterning offers a way to work from the inside out. I mean, imagine being able to actively prevent the formation of circuits that could lead to dangerous behaviors, or to directly write in structures that guarantee a model is robust or honest. It's a potential shift from just hoping a model behaves well to actually engineering the internal logic that ensures it. This research really opens up a door to a whole new level of control over how we build AI, and it leaves us with what might be the most important question of all. For the first time, we have a real tool that could let us write an AI's internal logic. The question isn't just, can we do it anymore? The question is, what should we tell it to think?